of this assignment, that is free running timer overflow. As mentioned earlier, the value of FRT is only 16 bits, which can lead to overflows happening quite quickly in human time. For both part A and B, since the FRT output is limiting, we don't really know when the event occurs outside of the current FRT interval. For this part of the assignment, we will add in code to extend the FRT by incrementing a 16-bit timer H and timer H for timer high. And when the FRT overflows, this can be done easily by adding in an ISR when the FRT overflows. Open this file in 3.11. You will need to copy your values from part B as well as add another one. A couple new variables have been added, itime h and otime h, to keep track of the higher resolution FRT. You will need to add in code in the main loop and IC3 and OC4 ISRs to print and capture the new timer. See the comments. The ISR for TOF is simple. When it happens, increment the 16-bit counter timer H. See the comments. When you run your code, the output will be same as the part B, except the FRT value will be 32 bits. Now over time, when you throw the switch, the upper 16 bits of the FRT should be changing, thereby giving us more information as to when the switch was changed. It should be noted that this doesn't increase the resolution of the OCs. If you want to do that, it will take more work to schedule when the OCX interrupts happen based on the upper 16 bits of the new FRT, but it isn't impossible. We won't be covering that here. Okay, now let's look at the coding. So this is what given, and here we have to adjust these 6 values. Is from the reference manual, you can get it, and I found it already. I just gonna put it right away. This one is 1 in binary, and then this one is 16 in binary, so this right here, and then this one is 8 in binary, so there should be a 1 here, and this one is 10 in binary, so 8 and a 2, actually 12 in binary, 8 and a 4, and then 3 in binary, so this is, and this one is this is 0 1 2 3 4 5 6 7, 2 power 7, that is 128. Okay. And that is basically it. These are the values that to be changed like that. And after that, here add your code from part B to add 4000 to itime and store it in a TOC file. So I'm going to open the part B. If you want to see my part B, you can watch my previous video. I did that over here, and here we did the addition of 4000. So to add 4000, what we do is we use the accumulator D, because 4000 in hexadecimal is like 16 bits. Each number in hexadecimal represents 4 bits, so 4 numbers, 16 bits. To add 16 bits, we can use the accumulator D. Accumulator A and B is not possible because those are 8 bits. Accumulator D is 16 bits, so we can use that to do this process. That's why we use LDD, ADDD, STD. We just use the accumulator D to do that. So I'm going to copy this one and paste it over here. Okay, now print the value for itime H here. Okay, to print that one out, we have to put a code for it. So to print that one out, what we do is we can do load accumulator D with itime H. Okay, let's comment this one as well. Plot the value of item h into the accumulator d. And then JSR, jump to the subroutine serial hex 2, that is over here, that does this process. It do the push that will remember 8-bit values, and then LSR 4 times. This will shift higher 4 bits to down 4 bits, and we need to do this 4 times because we don't have any other instruction to do this process, so we have to use this 4 times. And then branch to subroutine, that will go to serial hex 1, that is this, and do this process, and pull a restore it, follow through the next subroutine. Okay, that's what's happening here. We had to call that one over here. We have to jump from here to there. So you can see this iTime doing the same thing. Okay, we had to just follow through that. It's the exact same thing. The only difference is this is iTime h now, and we have to do exact same thing. And TBA is move accumulator B to accumulator A. Since we are doing accumulator D, accumulator D is basically a combination of accumulator A and a B. A takes the high bits, B takes the lower bits. That's why we switch accumulator B with A, because when we go to serial hex 2, that is only dealing with the accumulator A. So that's why we had to switch the B to A here, because then when we send again, that's going to change the B as well. Otherwise we cannot change the B separately because it's only dealing with A. Okay, now let's do that here. The exact same process for the serial jump to serial hex 2. So this one, exact same process, you can just copy. And then here also we have to use the TBA to do that, do the switching. Copy exact same thing, move ACCB to ACCA, and then JSR serial hex 2. That will print 2-digit hex value in a new ACCA. Okay, so that's for the iTime h. Print value of iTime h here. We did it like this. And here print the value of OTime h here. Exact same process. We just have to copy this one. You know, I can just literally copy this and then paste it here and change this one into OTime h. And in the comment I can output the time h here. This is overtime, this is overtime time h when interrupt proceed overtime. Print 2 digits of ACCA first, move ACCB to ACCA, print 2 digits of hex value to new ACCA. Exact same process. And then IC3 vect we have to copy from the previous one. This is my previous part B, and I did a part A and part B in a separate videos. You can watch them. You don't know what happened there. I copy this IC3 vect and paste it over here. and then this one remains the same, and then OC4 vector also I did in the previous video. You can watch it and understand. I just copy this one and put it over here, and that is it for this. And then we have serial hex2 and doing all this. Okay, that's B part, and we had to copy both of them. And what else? Copy timer h into O time h as well. Copy OCT. Okay, so we had to this add this timer h into O time h. So here we had to we had to do something for this. Okay, let me say look at the previous one, and here also we had to do this part. So there has to be done, some editing has to be done here in order to make that change. So first initially we load the accumulator with this, and then with this, T flag, I flag, and TCI3, I time, and after this we can do that. So I'm gonna load timer h here, LDD timer h. Here we load the value of timer h, register into accumulator D. And then std item h. I time h, okay. Here we are store the value, of the accumulator D into the item h variable. Okay, and others remains the same. Okay, and for the OC4 vector also we had to do the exact same thing. So I can literally copy this one and paste it over here. Here we have we do this one after I time. Here we can do this one after O time. Okay, I did that, and that is basically it. Then do we have to do anything else? Add GIS circle TOF. So here we have TOF vect provided, and it has some instruction. Check proper interrupt flag to make sure we should be here. Read T flag 2. Whenever they mention read, that's basically mean loading. So I'm gonna load that. LDA T flag 2. Load the value of load the value of T flag 2 register. into the accumulate array. And then AND it by mask bit. Let's look at the mask bits we have. So we have one mask bit that is dealing with the IC3, and one mask bit is dealing with the OC4, and we have another mask bit that is dealing with TOI, and the one we are dealing with right here is TOF. That's the one. That's the last one here. Okay, so we have to do the AND with this one. I copy that one, bring it to this. Here I'm doing. So doing the AND process, and a number sign, and then paste whatever I got it from there. This one, perform bitwise AND operation. With the mask is okay, and then if C flag is set, get out by going to fend. So Z flag is when it's 0, when it's equal to 0, we have to go to this. That's to achieve that we can use BEQ branch if equal to 0. So when C flag is set, that's going to be 0, so it's going to be branching. Where to branch? That is to fend. I put that one over here. So let's write the comment for this: branch to fend. If the result of the previous operation is 0. Okay, and then if so, clear the interrupt, write a 1 to mask bit in T flag 2. Okay, to clear the flag we use the store STAA T flag 2. That's going to clear it. Yeah, what we do is store the value of accumulate array back into the T flag 2 register. Okay, and then what else mentioned here? Increment 16-bit counter timer H. Okay, so to do the increment, what we can do is we can load X first, then do the increment, and then store. That's a 3-step process. Let's do that. LDX timer H. Here what you're doing is load the value of timer H register into the index register. And to do the increment of register X, we just use this one, INX, for the increment. Increment the value of the index register. Increment the value of the index register. Okay, and then store it in the X register, whatever the value. First we load and then increase, and whatever increase is going to be stored on the index X register as well. The STX to store in the index X register, timer age. Here store the value of the index register back into the timer age variable. Store. Okay, first we are loading the timer age with the X register, doing the increment and storing whatever the increased value to the timer age again. Store the value of the X register back into the timer age variable. Okay, so that is basically it. Now do we have to do anything else? Seems like that is it. There's nothing else has to be done. As I'm seeing, I'm taking care of everything. Now let's go ahead and run this code and see if we are getting any error. So I go to the execute, reset, and then run. Turn the switch on and off. It's working perfectly, giving zeros and ones. That's what has to happen. Okay, so that is basically it. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.